Hello. This is a slideshow presentation and demonstration for Scarlet Spacehawks, the NASA RMC team based out of Illinois Institute of Technology. I am Chris Sherman, a second-year computer science major, and this has been my first year on the robotics team. So this year, our team presents Clive, our second iteration of an AugerBot. It features a salvaged ice auger for digging, as well as an improved electrical system for organization and better organization of our code as well. Our mechanical team's goals this year were capability to drive on the simulant in the arena. So we did some things with our drive system for that. We needed to be able to extract the gravel from the environment, and we need to be able to unload that gravel into a collection bin after we have excavated it. Our drive system consists of 4 open wheels made of aluminum. Each wheel is fitted with 6 crossers that allow us traction as we go through the soil. Each wheel also has its own sim motor and feedback system, allowing for all-wheel drive. As for our excavation system, a major change that we made from last year was having our auger go through the middle of our robot instead of out of the front. This allows us better stability as well as a better payload delivery on our excavation. In order to accomplish this, our mechanical team came up with a system powered by 2 linear actuators that could change the pitch of our auger so that we can start out within our height constraints and then move to vertical mining, which, like I said, is better for our payload and stability of the robot. In order to move our auger up and down, we implemented a ball screw slider system for that. I'm going to hand it off to my colleague now to tell you a little more about the electrical system.
Hi, my name is Maggie Barclay. This is my first year on the team. I'm a freshman. I do community outreach and electrical. And for the electrical team this year, there were a few goals. Based on our performance last year, we figured that we had a box of our components and wires that was not easily accessible. So if we needed to fix anything within the robot or test something, we couldn't easily access our components. So one of our goals this year was to have an easily accessible e-box. So we used a server rack type e-box in order to get that easy accessibility. We also wanted to make it completely dust-proof, which this rack also helps with. So these were a few goals that we had this year. Now, in order to increase the manageability of the wires, we also iterated our first design of a PCB board. So for the PCB board, it simplifies the connections from the Arduino and the Tinker board in our system to the sensors. So this negates the option of having a bunch of wires go to and from places in the electrical box. So this just simplifies and cuts down the amount of wires that we need. There's also the auger circuit is based out of the PCB board. With the auger circuit, there were a few things that we needed to keep in mind. We needed isolation between the high and low power systems, which we used an optocoupler for. In the lower right-hand side, or lower left-hand side of the slide, you can see the optocouplers in a soldered circuit for the auger circuit. This soldered circuit was used before the PCB came, before it was completed with its design in order to test the circuit. Once we knew that the circuit was working, we were able to implement that into the PCB design and use that. That's basically how we tested our auger circuit. I'm going to hand it back over to Chris for programming.
So our programming team had a few goals this year. One of those was modular design, allowing us to better organize our code and be able to build our code off of code that was already written. We wanted a customizable control over mechanical parts so that it could be used in a variety of ways, including manual control using commands, and also worked into our autonomous programming. And then, of course, that third goal is autonomous programming. For our robot control, a lot of our high-level commands and control come out of the Tinker board. Through the Tinker board, we are able to accomplish things such as Wi-Fi, SSH, and that autonomy processing that takes a little more power. This Tinkerboard will send commands to our Arduino Due, which will provide for control over a lot of our moving parts, such as the motors and actuators that we have on our robot. The Arduino interfaces with kangaroos via a multi-kangaroo serial line, allowing us to send commands to them and receive feedback from the motors, allowing us to do cool things such as synchronizing the linear actuators for our auger mount. The one exception to this is our auger drill, which sends the signals are sent straight from the Arduino and do not go through a kangaroo. Our autonomy was developed in 2 phases, the first of which is accomplished without any information on the arena. In order to gather the information, we would need to traverse the area first and collect data using the sensors on the robot, while also assigning coordinate systems based on referencing with our location system that was built into the robot as well. Our second phase is once we have reached our destination, and we get a chance while we're mining to process all the data points that we collected on our way. This will allow us to simplify all of the obstacles that we detected into circles with a center coordinate and a radius. These values can then be fed to an A-star search algorithm, which we are using to provide pathfinding for our robot. Pathfinding will allow us to find a safe and efficient way back to our collection bin and allow us to get back for our materials. Everything after phase 1 can be accomplished through pathfinding without brute forcing our way through the arena. In order to gather our information on the arena, we used a LiDAR sensor. Now, our system with the LiDARs is twofold. The first is mounted to the back and it's mounted horizontally. It uses the ability to range find and track the light sensitivity of the reflective surfaces it touches. To track a target, which provided for an origin for our static coordinate system, for which we would reference the robot and the obstacles around it. Now, our second of these LiDARs is mounted to the front at an angle. This allows us to look from the mounted LiDAR all the way to the ground, and because we are detecting the ground, we can detect the variations and distinguish them from just another wave in the sand or a rock that we might potentially have to avoid. And these 2 were implemented in order to gather that data so that we could form our autonomous program. I'm going to hand it back to Maggie to talk a little bit about our team and safety precautions.
So our team this year was made of about 20 students from diverse majors. We had computer engineers, electrical engineers, mechanical engineers, computer scientists, and they all came together to work in this project in different areas of it, come up with one complete robot. Our faculty advisor was Dr. Mahesh Krishnamurthy. We just want to thank him for his support and guidance. Now that we know a little bit about the team, let's move on to the safety precautions of our robot before we do a demonstration. So in order to be safe around this robot, we need to know where the hazard points are. The first point of hazard is the wheels. They're made completely out of metal and they're very sharp, especially around these areas. So we need everybody standing back from the robot when it's moving. The second point of hazard is the auger itself. So even though there's this metal sheath over it, it's still dangerous here at the bottom where it's actually excavating through the soil. So this is very sharp, and we also need everybody standing outside of these areas when the robot's moving. The last point of hazard is the linear actuators. So the linear actuators change the angle of attack of the auger, and they can easily crush what's ever behind them, so we need all hands off the robot when it is going to be demoed. Now, when the robot's actually going to be demoed, we need everybody wearing safety glasses in order to protect their eyes in case anything goes flying, just as a safety precaution. Now, if anything bad happens during the robot's running time, we have 2 ways to stop the robot. We have an onboard e-stop, which is easily visible and accessible for whoever's on that side of the robot. If anything were to happen, somebody could easily press the button and the robot would completely halt motion. Now, if someone is far away from the robot and notices that something is going wrong, we also have a remote e-stop made out of an old-fashioned key fob that can stop the robot at a distance. So you don't necessarily need to be close to the robot to stop it. Now that we know a bit about the safety precautions of our robot, let's move on to the demonstration. So at this point, you should be seeing a video that shows the drive system working and the wheels turning. And at this point, you should be seeing the auger moving and changing the angle that the auger is at. And now you can see the conveyor running and dumping and running in order to dump the soil. So now that we've seen the demonstration of our robot, I'm going to hand it back over to Chris for some final words.
So just some final words. A special thanks to our faculty advisor, Dr. Mahesh Krishnamurthy, for all of his guidance this year, and also for all the support that he gives our team. Special thanks to some of our sponsors, including SolidWorks and Advanced Circuits, for their contributions to our team, and a special thanks to Illinois Institute of Technology as well for the funding that they provide for our team. We would not be able to do a lot of what we do without them. And of course, special thanks to the people at NASA for organizing this competition and allowing us to express our love for technology through making our robot. This has been Scarlet Spacehawks. Thank you for watching.